All right, let's get started. So last week we started number theory. Today we're going to be just continuing with number theory. First we'll be doing things with the greatest common divisor. You all know the greatest common divisor. You talked about the greatest common divisor all through grade school, right? And then next we'll be talking about modular arithmetic. That's just going to be doing basic arithmetic with a really small set of numbers. Just a couple integers instead of having to use all the integers. So those are the two big things that we're going to cover today. Now for greatest common divisor, it's very, very, very important that you remember the main theorem we did last week. It's going to show up in all of number theory over and over and over again. So do we remember what the main theorem was last time? The theorem about division. If I have two integers, a, b, with b greater than 0, what do I know? That there exists two unique integers, q, not g, q and r, such that a is equal to qb plus r, where what?
Where r is the remainder and q is the quotient.
That's our name for them, but where r is in between 0 and b. We don't let our remainder, so yeah, we call that the remainder and the quotient. We don't let our remainder be a number bigger than b, and we don't allow for negative remainders. You remember that?
Mm-hmm.
And then we introduce two operations. We introduced the operation a div b. What was that? That was the quotient q when you write it out this way. And we introduced a mod b. Those would be in computer science. It's exactly what you used with mod. It's exactly what you meant by mod. And that's the r, the remainder. Okay, those were the big ideas last time. So now, today, we'll begin with talking about the greatest common divisor. So, first off, what's a common divisor? Let a and b be integers. We call d in z, we call d the integer d, a common divisor of a and b, provided that d divides a and d divides b. If d divides both numbers, d is a common divisor. New information, right? Okay, next. Let a and b be integers. We call the integer d the greatest common divisor. I'm going to use GCD throughout this whole lecture, so greatest common divisor every time you see that. So we call the integer d the greatest common divisor of a and b, provided that two conditions are met. First of all, d is a common divisor of a and b. It can't be their greatest common divisor if it's not a common divisor. So first off, d is a common divisor. And secondly, if e is also a common divisor, then e is less than or equal to d. In other words, d is the greatest common divisor. Any other common divisor is less than or equal to d. You can't get more than d if you're a common divisor. D is the greatest common divisor. All making great intuitive sense? Mm-hmm. All right. So notation. We view GCD as a function. GCD, it eats up two things and it spits out the greatest common divisor. This is the greatest common divisor function. From now on, GCD of two numbers is the greatest common divisor. So here I'm saying D is equal to the greatest common divisor of A and B. Good? Notation we're going to use from here on out. Okay, so let's do our first proof of the day. Let A and B be positive integers. You comfortable with that notation? I'm not sure if I've used it in here before. Let A and B be positive integers, and let C equal A mod B. In other words, C is a remainder when you divide A by B. Good so far? Yeah. Okay. Then, the greatest common divisor of A and B is also the greatest common divisor of B and C. So the greatest common divisor of A and B is the greatest common divisor of B and A mod B. That's what we're going to prove. Now, why are we going to prove this? Oftentimes, we're going to, from here on out, through number theory, a very useful thing to do a lot of the time is to calculate the greatest common divisor between two numbers. And this is going to help us calculate the greatest common divisor between two numbers. It's going to help us go from working with really big numbers to really small numbers. Because in general, C, the remainder, when I take A and I divide by B, the remainder is going to be small relative to A and B, as a general rule, right? The remainder is much smaller. So, for example, we'll prove this later, but let's use it real quick to help you wrap your head around what's going on here, and then we'll go back and prove that. So, say I told you to find the greatest common divisor of 689 and 234. Obviously, that's not trivial, right? So, but what do I know? I know that the greatest common divisor of 689 and 234 is the same thing as the greatest common divisor of 234, and the remainder when I take 689 and I divide it by 234. So I may calculate now this thing. I'm going to figure out what C is. So I'm going to take A modified by B, which is going to give me C, and then I can just calculate this greatest common divisor now. So what is C? So here's my A. A is equal to 2 234s plus 221. There's my remainder. Right? A is equal to QB plus R. You with me so far? Mm-hmm. So what our theorem is saying now is that the greatest common divisor between these two numbers is also the greatest common divisor between these two numbers. Alright, so now I just need to find the greatest common divisor between these two numbers. But our theorem says that if I take this number and divide by this number, I'll get a remainder. So take this number, divide by this number, I get a remainder. And it says that the greatest common divisor of these two numbers is also the greatest common divisor of these two numbers. And once again, if it's not obvious to you yet what the greatest common divisor is, do it again. The greatest common divisor between these two numbers is also the greatest common divisor between these two numbers when I divide. So I take these two numbers and I divide, and I get my remainder 0. So now the greatest common divisor between these two numbers is the greatest common divisor between these two numbers. What is the greatest common divisor between 13 and 0? 13. 13. Right? 0 is divisible by any number. Right? This isn't divided by, this is divisible by. 0 is divisible by any integer. You can always find an integer. For any integer you pick, 279, I just picked a random one, I can always find an integer, x, such that 279 is equal, wait, am I saying that wrong? 0 divides any integer, sorry. 0 divides any integer. Because 0, I can always find, why am I saying this wrong over and over again? The greatest common divisor of those two things, every number is a divisor of 0. That's all I'm trying to say. For any number, I can multiply an integer by an integer and get 0, namely 0. That's all I'm trying to say. I feel like I kept saying it wrong. That's it. So, the greatest common divisor is 13. The greatest common divisor of these two numbers is 13.
That's so cool.
Yeah.
Why didn't we get taught this like
Well, I don't know. That's not a question I can answer. Anyways, so in short, the GCD of these two numbers was 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 13. That's what our theorem gives us. So it gives us a way to keep reducing the numbers we're taking the greatest common divisor of until it's obvious to us what it is. Okay? So that's the usefulness of it. By the way, this algorithm right here is called Euclid's algorithm for finding the greatest common divisor. We just call it Euclid's algorithm because if you go through the elements, Euclid gave that exact algorithm for finding the greatest common divisor between two numbers. He did it with geometric figures, but it was the exact same idea. So if I accidentally keep saying using Euclid's, I mean using this method right here. All right, let's go over our proof now. So let A and B be integers, and let C be the remainder of A when you divide it by B. Or C is equal to A mod B, same thing. Then the GCD of A and B and the GCD of B and C are equal. That's what we're proving. Now going back to last week, we know, notice that A and B are positive integers. All we care is that B is positive. So since B is a positive integer, then there exist integers Q and C such that A is equal to QB plus C. right? Where C is between 0 and B. And that C is exactly what this is. So, in other words, there's this relationship between A and C. If I know that C is equal to A mod B, then I know that there exists some integer Q such that A is equal to QB plus C. You good with all that information? Nothing weird there? We're just going to reference that throughout the proof. So, let D be the greatest common divisor of A and B, and let E be the greatest common divisor of B and C. Remember, what we're trying to prove is that these two are equal. So, and it remains to show that D is equal to E. That's what we're trying to prove. Trying to prove that this GCD is equal to this GCD. We're calling this one D, we're calling this one E. We're going to prove that they're equal. How are we going to prove that they're equal? I'm going to prove that D's less than or equal to E, and E's less than or equal to D, therefore they're the same. Good? Alright. So, first we're going to prove that D is less than or equal to E. Observe that D divides A and D divides B. How do I know that? D is the greatest common divisor of A and B. So D divides A and D divides B. It's their greatest common divisor, so it divides both of them. Right. Alright, you with me so far?
Yes.
Alright, now what does it mean for D to divide A? That means you can find some integer, call it K sub 1, such that A is equal to K sub 1 times D. What does it mean for D to divide B? It means that you can find some integer, call it K2, such that B is equal to K2 times D. With me so far? Okay. Don't lose track of what we're trying to show. We're trying to show that D is less than or equal to E. So I need to bring E into this expression somehow. And E is related to C, so I need to bring the C in. So I know D divides A and D divides B, which means I can write A and B in terms of D. That's all I'm saying. Now, what do I know about C? C is equal to, this is just reworking the algebra of this equation a little bit. Okay, so C is equal to A minus QB. In short, all I'm going to say is, look, C is equal to something that's divisible by D and something that's divisible by D. Therefore, C is divisible by D. That's what we're doing in the algebra here. So C is equal to A minus Q times B. But A is the same thing as K1 times D. And B is the same thing as K2 times D. Factor out my D's. You with me? So, therefore, D divides C. So I knew that D divided A and D divided B. Now I showed D divides C. So in other words, I now know that D divides both B and C. So D is a common divisor of B and C. E is the greatest common divisor of B and C. D is a common divisor of B and C. Therefore, D is less than or equal to E. D is a common divisor. E is the greatest common divisor, therefore D is less than or equal to E. Okay, so we showed D is less than or equal to E. Now we're going to show E is less than or equal to D, and therefore they're the same. So continuing. Observe that E divides B and E divides C. Well, how do I know that E divides both those?
Because E is a common divisor, well, the greatest common divisor.
E, by definition, is the greatest common divisor of B and C. Therefore, E divides B and E divides C. What does it mean for E to divide B? It means that E times some integer equals B. And what does it mean for E to divide C? It means E times some integer equals C. These K1s and K2s are different from those ones. Just reusing variables. Okay. So now we need to show that E divides A. Well, A is equal to QB plus C. And we know that B is the same thing as some integer times E. And we know that C is the same thing as some integer times E. Factor out the E. What did we just really show? We just really showed E divides A. So E divides A and E divides B. So E is a common factor, or a common divisor of A and B. D is the greatest common divisor of A and B. E is a common divisor of A and B. Therefore, E is less than or equal to D. They're less than or equal to each other. Therefore, they're equal to each other. Follow the logic there?
Yeah.
Pretty straightforward proof. Okay, this is the proof behind Euclid's algorithm. It's what drives Euclid's algorithm. There's two proofs in the book that, unfortunately, I had to go past for the sake of time, and it just uses this proof behind the scenes, so I think you could understand it if you just read through it. It's just kind of wordy, handling the cases. All it proves is, one, that Euclid's algorithm does give you the greatest common divisor, and it's just using this behind the scenes. You notice that's exactly what we were doing here, right?
Mm-hmm.
And then two, the second thing it proves, which isn't as trivial, is that Euclid's algorithm not only gets you the greatest common divisor, but it gets you the greatest common divisor really fast. Really fast. And I think the numbers that the book took the time to calculate is, if you have two numbers on the order of magnitude of 10 to the 1,000, now I do not know how to make this number make sense to people. Roughly speaking, there is 10 to the 80 atoms in the universe, in the observable universe. Okay?
Mm-hmm.
So take all the atoms in the universe, and now multiply it by 10. And you just switch this to an 81. Now take that number and multiply it by 10. You just switch this to an 82. This is taking too long. Take that number and multiply it by 1 billion. You just switch this to an 89. Okay?
Oh my god.
That is such an absurdly massive number, I don't even know how to make it sink in how massive numbers like this are. Euclid's algorithm can find the greatest common divisor of two numbers like this in roughly 7,000 steps. You'd have to do 7,000 of these lines to figure it out. Which is a very, 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 very small number compared to this. Yes, two numbers this big, try and find the greatest common divisor. It'll take you roughly 7,000 steps. The way that you probably found the greatest common divisor before is some sort of naive way where you keep trying all the numbers up to this number, looking for whichever one's the biggest.
Yeah.
If you tried to do that with numbers like this, even if you wrote a program to do that on a super fast computer that you had at the instant of the Big Bang, and you let that computer run throughout the entire life of the universe all the way to its heat death, it wouldn't come close to finishing the job. And yet, using Euclid's algorithm, we can do it in 7,000 measly steps. You can get a computer to do this like that. Well, kind of like that. The hard part's getting you to hold numbers that big. But outside of that, a computer that was specifically built to do this could easily do it. So it is a very, very, very fast algorithm, and for really big numbers, it reduces the problem and makes it manageable really quick. It decreases exponentially. Basically, every 2 steps the algorithm runs, it divides the numbers you're working with by 2, is what you essentially prove. Okay. So now, this one I already had written out for you, but let's actually use Euclid's algorithm now to find the GCD of these 2 numbers. I just picked 2 numbers, so hopefully it comes out nice. This wasn't in the book, I just want another example. So, we're going to find the GCD of these 2 numbers. What do? We need to figure out their remainder. So, let's see. 616 is equal to what? How many of these can I get?
5.
5 of them. And what will my remainder be?
91.
91?
I think.
Let's see. Multiply that by 5, we get 525. Plus 91, 515, 516. I think you're right. Alright? So now, the GCD, we know that the GCD of these 2 numbers is the same as the GCD of these 2 numbers. Right?
Okay.
Yeah.
Okay. So now, we're right so far. So now, 105, if you can't see what the GCD is already, then we'll rewrite it again. So between these 2 numbers, what do we get? How many times does 91 go into 105?
1.
Once, with the remainder of what?
14.
14. Okay. Now we need to find the GCD of these 2 numbers. 91 is equal to how many 14s?
7.
7 14s?
Wait, no, not 7. 6.
6 14s? Does everyone agree with that?
I guess so.
Let's let other people think about it for a second. What do you think, Rhoda?
I think it's 6.
You think 6?
Yeah.
What's 6 times 14? See if you actually did it.
6 times 14 ends in a
start with?
7.
Almost.
8.
There you
7.
go.
No, it's 7. 8. Oh, what is it?
So what was your number now?
78.
How many times does 14 go into 91?
6.
6. Okay. There you go. So you can use 2. So 6 times 14 was what?
78.
78?
Yep.
Wait, what?
I thought it ended in a 4. Oh, 74. It's 84. How did that keep going?
84. 84. And what's the remainder?
7.
7. So now the GCD of these two numbers is the same as the GCD of these two numbers. What's the GCD of these two numbers? 7. Can everyone see that okay? Or do we need to do one more step?
No, it's fine.
We can do one more step. 14 is equal to 2 7s plus 0. What's the GCD between these two numbers?
7.
7. Okay, so our GCD overall, this is equal to 7.
Woot woot.
Okay? You are, A, going to have to calculate on your test the GCD of two big numbers, and B, will not be allowed a calculator.
Mother sucker.
Yes,
So
sir.
that's coming down the pipeline. So you better know how to use this algorithm.
Okay.
Okay. Furthermore, there's going to be proofs where you have to use this algorithm in an extended way. We call it extended Euclids. That even if you decide to somehow cheat and Google GCD and find the GCD that way, if you didn't use this algorithm, you're going to be lost how to continue, because we're going to use this algorithm in reverse afterwards to find some other cool stuff. So you better know this algorithm. There's no way around it.
It's pretty easy.
Because I can easily give you big numbers that a computer can't handle to know how to just give you the answer to. So,
You're going to give us numbers that a computer can't handle?
not without you telling it how to handle it. Give you problems to solve that a computer can't naively just solve.
Why?
So if you just Googled it, you won't be able to
How
find
do
the
you
answer.
do that?
Well, one, you wouldn't have known how to find the GCD of two numbers without some program that knew how to do it. So maybe now you know in your head, okay, I'll go Google specifically greatest common divisor calculator, and now you can find one. Yeah. But for the next part, we'll see if you can find a calculator to do that.
Oh, seriously.
All right. Anyways, continuing. So now we're moving up to the second, probably the second, most important theorem in all of number theory. Coming up. Let a and b be integers not equal 0. Then the smallest positive integer of the form ax plus by is their greatest common divisor of a and b. Let me say that one more time. Let a and b be integers, not equal 0. So you have a and b, they're integers. Okay, those are given. Now I tell you that plug in integers x and y, plug in all possible combinations of integers x and y in existence, and evaluate this expression. The smallest positive number that comes out of here is the GCD of a and b.
Okay.
Let me give you a more concrete example to help it sink in before we prove it. Let's say that a is 30 and b is 24, just two numbers. With me so far? So now we're going to look at ax plus by for just a bunch of integers. Obviously, we can't plug in all of them. To help you see that the GCD is the smallest positive integer you get out here. So here's my x's, here's my y's. I'm just plugging them in to this equation when a is 30 and b is 24. So if a is 30 and b is 24, plug in negative 3 for x and negative 3 for y, you get this number. Plug in negative 3 for x and negative 2 for y, you get this number. You with me on what this is doing? Plug in 0 for x, 0 for y, you get this number. So 0 is the GCD of these two numbers, right?
No, because they can't be both 0.
But I'm saying when you plug in 0 for x and y. Good, you're confused. Now you're thinking about it. Okay, so let me read the theorem one more time, then you can look at this table, and then tell me why 0 isn't breaking anything. Let a and b be integers not equal 0. Then the smallest positive integer of the form ax plus by is the greatest common divisor of a and b.
Zeros are the x and y.
Zero's not.
Positive! The smallest positive integer of this form. 0 is not a positive integer. So if you were to expand this table out to infinity, calculating all these, you see that the smallest positive integer that shows up is 6. So 6 is the GCD of these two numbers. Do you know what this table's showing?
No.
Okay. We picked two numbers for A and B. So now we have 30x plus 24y. So that's this equation, plugging in 30 and 24 for A and B. You with me so far? Now, what would I get if I plug in 0 for x and 0 for y?
You get 0.
You'd get 0. That's right there. What would I get if I plugged in 0 for x and 1 for y?
You get 24.
What would I get if I plugged in 0 for x and 2 for y?
Okay, so... Okay, I get it.
So these are all the numbers you would get plugging in different combinations of x's and y's. You with me? So what we're saying is, if you were to expand this table out to infinity and do it for every possible combination of integers, the smallest positive number that would ever show up is 6. And you get to show up in the table all over the place, but the point is the smallest one that would ever show up is 6. You would never get one smaller than that. That's what we're proving. I know this one seems weird, and how on earth is this going to be useful? But I'm telling you right now that this theorem is probably the second most used theorem in number
So
theory.
you have to draw that box every single time?
No, you will never dry out of this box again.
Okay.
This was just to help you understand. Look at my proof, there's no box. But do you understand what it's saying? That's the important part before we prove it. Alright, then let's prove it. Oh, one note I want to make before we proved it. It is absolutely impossible for us to get a positive number ax plus by less than the GCD. So we said that the smallest number that will show up on here is the GCD. We're going to prove that the GCD would eventually show up. It is impossible for a number smaller than the GCD of A and B to show up in this form. How do I know that that is impossible?
Because if it...
Look, the GCD of A and B is a divisor of A and it's a divisor of B, right? So it's a divisor of this whole thing, right?
Yeah.
Therefore, this integer, whatever it is a multiple of our greatest common divisor. It's either 0 of them, or it's 1 of them, or it's 2 of them, or it's 3 of them, or it's 4 of them. It's some multiple of them, right? It's not 0 of them, since it's more than 0. But it's less than 1 of them, since it's less than 1. What's the integer I can multiply it by to get more than 0, but less than 1? You can't. Does that make sense?
I think so.
Okay, so we're proving that the smallest positive integer you can get out of here is the GCD. We already know right out the door that you can't get something smaller than the GCD out of there, but maybe you couldn't even get the GCD out of there. We're going to prove that you can. And furthermore, we're going to find a way to calculate the x and y that give you the GCD using extended Euclids. Yeah. Alright, so let's do the proof real quick.
Right, we need to know that x and y.
Huh?
We don't need to know the x and y.
It is very useful to know the x and y.
Why?
You'll see. I can't motivate number theory ahead of seeing it. I don't know how to do that. Okay, so let A and B be integers not both 0, and let D be the set of all the numbers that are of this form when you plug in any values for x and y that you want, but we require them to be greater than 0. Okay? So we're picking all the numbers off this table that are greater than 0, and we're putting them in a set called D.
Okay.
You with me so far? We're going to define the greatest common divisor to be the smallest element in this set. Okay? So, if we're going to define the greatest common divisor to be the smallest element in this set, first thing we need to do is show that this set is not empty. I need to prove that there's at least one positive number in there. I need to prove that there's some x and y I can find in the integers, such that when I plug those x and y's into this equation, I get positive numbers. Now, how am I going to do that if I don't know anything about A and B? What's the magic numbers I can plug in there? The magic numbers are, pick A for x and B for y. When I plug in A for x, what is this term? A squared. Is a square ever negative?
No.
No. When I plug in B for y into this term, what do I get?
B squared.
B squared. So now I have A squared plus B squared. That's always a positive number. Why can't it just be 0? Can't I just plug in, can't A and B be 0? No, they're not both 0 by assumption. At least one of them is non-zero. So when I square one of them, I'm guaranteed to get a positive number. So observe that A times A plus B times B is greater than 0, so D is not empty. All that's just say D is not empty. That's all we're trying to say. Since D is not empty, and notice also D is only positive integers, right? So it's a subset of the naturals. So D is a non-empty subset of the naturals. D is a non-empty set of natural numbers, is another way to say that. Everything in D is positive integers, and it's not empty. Therefore, by the well-ordering principle, D has a least element. We'll call it little d. Okay? So far, little d is something in here, and it's the least thing in here. That's what we have so far. Now we're going to show, it remains to show that D is the GCD of A and B. We need to show three things. We need to show that D divides A, we need to show that D divides B, and then we need to show if something else divides A and B, it's less than or equal to D. Those are the three things we need to show. You with me? So first I'm going to show D divides A. I'm going to do this by way of contradiction. To show D divides A, assume by way of contradiction that D does not divide A. If D does not divide A, what does that mean? It means when I do A divided by D, I get a remainder. It doesn't go in evenly. There's a remainder when you do the division. Does that make sense?
Yeah.
So then, there exists Q and R such that A is equal to QD plus R, with R between 0 and D. Now, remember from last week, our formula says R greater than or equal to 0 and less than D. But since we know that D does not divide A, then this R is not 0. The fact that we erase that little underline is a huge difference. Okay? So R is a positive number, and it's less than D. I'm going to show that R now is also in this set D. That's going to be my contradiction. Little d is the smallest thing in there. R is another positive integer. I'm going to show it's also in there. Contradiction, because R is less than D. That's going to be my contradiction. So I'm going to show that R is also in this set. Contradiction. You with me? Okay, so what is R? Just look at this equation, do a little bit of algebra, there's R. R is equal to that. But we know that D is in this set, right? We know little d is in this set. So we know that there exist some integers x and y such that d is equal to ax plus by. So I know that I can write d of this form for some integers x and y. You with me?
Yeah.
Okay. So, I'm going to collect my a terms and collect my b terms, and we're done. So how many a's do I have? I have one a, and I have negative qx a's. So I have 1 minus qx a's. Factor an a out of this term is where my 1 comes from. Factor an a out of this term is where my negative q times x comes from. With me on that? And then how many b's do I have? I have negative q y b's. So plus b times negative qy. What did we just show? We just showed that r is equal to a times an integer plus b times an integer, where r is greater than 0. D is the set of all numbers that can be written as a times something plus b times something, where it comes out greater than 0. R is greater than 0, and it can be expressed as a times something plus b times something. Therefore, R is in D. Contradiction. Because D was the smallest element in big D, and we showed that little r is in big D. Contradiction. Because it's less than it. Everyone understand that proof? That piece of the proof. We're not going to prove that D divides B. It's identical. So we'll skip that part. And we'll go straight to, therefore, D divides A and D divides B. You with me so far? So we showed that D is a common divisor of both these things. Now we need to show it's the greatest common divisor. So, let E be any common divisor of A and B. I need to show that E is less than or equal to D. Then we're done. If I can show that any other common divisor, E, is less than or equal to D, then D is the greatest common divisor. Okay, so let E be any common divisor of A and B. Then E divides A and E divides B, which means what? E divides any integer times A plus any integer times B. If I know that E divides A and B, then I know E divides anything that looks like this. Right? But that is D. So I know E divides D. You with me? So D is positive, and E divides it. So, oh, I said it here. Since D is greater than 0, then E is less than or equal to D. If I have an integer divides a positive integer, then we know that E is less than or equal to D. We already did that for every guy. Good? Okay. Therefore, D is equal to the GCD, and we're done. That's it. If you can wrap your head around that proof, you're good for this section.
I'm still a little confused on how you got E divides AX plus B1.
So E divides A and E divides B.
Yeah.
So that means A is equal to E times something, and B is equal to E times something.
Okay, but...
Now plug those values in here. And you'll get an E in this term, and you'll get an E in this term.
Okay.
It's the exact same thing we did over here, I just didn't want to drag it out. Since D divides A and D divides B, then I know D divides some addition of two terms that have A and B in it. You're saying that's a subtraction, but we can think about that as plus and negative times B. So since D divides A and D divides B, I know D divides this thing. How do I know that? Here I did the algebra the longhand way. Actually figured out what A is, figured out what B is, plugged them in, show, yep, D divides it. You can do the same thing there.
Okay.
Any other questions? Okay, so we just barely showed that for any integers A and B you choose, then there exists an x and a y such that A times x plus B times y gives me that GCD. Our problems now are going to be find the x and y such that this gives you the GCD of those two numbers. So I'm going to give you an A and a B, and I'm going to say find the x and y such that A times x plus B times y gives you the GCD of those two numbers.
You mentioned before that there are multiple different pairs of x and y that could give us the GCD.
Yep, so find a pair. Because once you get one pair, you can just do the same linear combinations of those pairs. Yeah. Okay, so how do we do this? We use Euclid's. Once again, this is called Euclid's extended algorithm. So same exact numbers that we had before, over here. We're using over here. And then we'll do an example that's completely different to see it again. But first, let's walk through everything right now. So I want to find the x and the y such that 689 times x plus 234 times y gives me the GCD of these two numbers. Now we know that the GCD of these two numbers is 13 already. So I probably wouldn't have given it to you like that. I would have said something along the lines of find x and y such that this plus this is equal to 13. That's our job. You with me so far?
Mm-hmm.
First thing we do is exactly like what we did over there. We find the GCD. So 689 is equal to 234 is plus 221. So the GCD of these two numbers is the same as the GCD of these two numbers. The GCD of these two numbers is the same as the GCD of these two numbers. GCD of these two numbers is the same as the GCD of these two numbers, which is 13. Same thing we did over there. Now, I put a vertical line, and I solve for the remainder in each line, keeping my numbers grouped together. So, since 234 is equal to 1 times 221 plus 13, then 13 is equal to 234 minus 1, 221. You see what I did on that line?
Yeah.
You can do the exact same thing on this line. Since A plus QB equals C, C is equal to A minus QB. Keeping my Q's and my B's together. Do not do the algebra on these terms and figure out what exact number that is. Keep the numbers grouped like this. Here's why. I am trying to write 13 equals something times 689 plus something times 234. That's what I'm trying to do, right? So 13 is my GCD, so find my... We could have also, you might be wondering, why didn't we do 0 equals 221 minus 17 times 13. We could have if we wanted, we're just not going to use that line. So step 1, find the first item in this list that uses our GCD, 13. So I know 13 is equal to 234 minus 1, 221, right?
Mm-hmm.
But now look at the smaller of these two numbers. What's the smaller of these two numbers?
221.
221. That means I have a substitution in this side of the list for 221. And 221 is equal to 689 minus 2 times 234. So I'm going to replace my 221 with this exact thing. You with me?
Yeah.
So that would be what one line looks like. Then we go down to the next line and we simplify what we had here. So I count up how many 234s I had. How many did I have? I have 1 here, and I have negative 2 here, for a total of 3 234s. Now, how many 689s I have? I had -1 689s for a total of -1 689s. Now that one, we already are done now. We have 13 equals something times 234 plus something times 689. Exactly what we wanted. So we have our x and our y. Now this one, the algorithm ended kind of quickly, so we'll do another one to try and help you see it all happening.
That's so cool though. It's genius.
Yeah, very quick. Ready?
Yeah.
Okay, so let's do this one. So I want to find the x and the y such that the linear combination of these two gives me 1. Spoiler, 1's going to be their GCD. But we still need to figure out their GCD so that we can get this side, so that we can back substitute and get the numbers. That's why I'm saying you better know how to do the GCD, because you're going to add on to that to find some numbers later. So even though we know what the GCD is, we're still going to go through Euclid's. It's still useful for what we're trying to do. So let's begin. 431 is equal to how many 29s?
Is it like 13?
I don't know. Is it?
I say 14.
Well, let's start with 15 then. Let's see. 29 times 15, what do we get? 9 times 5 equals 45. 40. 1, 4. And then we have 0, 9, 2. What do we get? 5, 3, 4. Just over. You were right. So we had 1 too many 29, so take away 29 from that, and what do we get?
No.
What's 435 minus 29?
406.
No, no, no.
Oh, 406. You just said that right. Okay, there we go. So, 406, so what's our remainder going to be? So, 431 is equal to how many 29s? 14 29s plus what? We're trying to get to 431. That goes to 406.
25.
25, thank you. 25, so let's erase this stuff. and put in 25. Okay, so now the GCD of these two numbers is equal to the GCD of these two numbers. You'll notice I always put parentheses here because it's possible that when we do this, this number could be bigger than this number. Don't lose track of what your A is, what your B is, and what your remainder is. Our algorithm says that the GCD is equal to the GCD of these two. It says nothing about that number. Okay. So now, 29 is equal to how many 25s?
1.
Plus?
4.
And now, 25 is equal to how many 4s?
6.
Plus what?
1.
1. And now we're done. The greatest common divisor is obviously 1, right? So now, I'm going to do extended Euclids, where we solve each one of these for their remainder, in terms of their remainder. So the top line, we say 25 is equal to 431 minus 14 29s. 4 is equal to 29 minus 1, 25. And then 1 is equal to 25 minus 6 4s. Right? So now we want to express 1 in terms of 431 and 29. We have 1 in terms of 25 and 4. We'll substitute the 4 to express it in terms of 29 and 25, and we'll substitute for the 25 to express it in terms of 29 and 431, and then we're done. So 1 is equal to 25 minus 6 times 4. What's the smaller of these two numbers?
4.
4. So that's what we're going to substitute it for. We better have that as a number right above it, in other words. That's another way you could look at it. Just look at the number right above and do that substitution. So this is equal to 25 minus 6 times 4. It's hard to spell. Alright, now we'll simplify. Simplify this expression, and now we're going to express it in terms of 25s and 29s. How many 25s do we have?
7.
We have 1 here, and then we have minus 6 times minus 1 is positive 6, so we have a total of 7. So we have 7 25s. And how many 29s do we have?
6.
Negative 6, right?
Yeah.
So plus, we can do negative 6 like that if you want, 29s, or we could have just said minus 6 29s. I think I'll just stick with the minus 6. Minus, but keep those numbers in parentheses so that you keep track of what you're expressing in terms of 25 and 29, right? So now, we're going to substitute out our 25s is one way you could look at, where you can say what's smaller out of these two numbers, 25, and do your substitution. Let me once again write that smaller so that we actually have space. So we have 7 25s minus 6 29s. And that is equal to, substitute our 25s in, so we have 7 25s. Oops, substitute our 25s in. 7 25s. Seven 25s minus 6 29s. With me?
Yes.
Okay, now, simplify. We have 1 is equal to, how many 431s do we have? 7. Plus, how many 29s do we have?
A lot.
We have negative, how much is that?
88.
No.
98.
98, good job. So we have 98 here, negative 98, and we get minus 6 more. So, looking back where we started, x equals 7, y equals negative 104. Those are the x and y's that make that equal to 1. Right? Good luck trying to figure that out by hand.
You just did.
Without the algorithm.
Why did you do that?
I think this one was an example, so we should be able to check to make sure we didn't make a mistake. Negative 104 and 7. Is that what we got? Awesome. Okay, so that is using extended Euclids to find the x and y to satisfy the equation. All right. A definition, a corollary, and then a quick proof, and we're done. So, definition. If the GCD of two numbers is equal to 1, then, that should be a then A and B are relatively prime. Two numbers are relatively prime if their greatest common divisor is 1. So notice all prime numbers are relatively prime with respect to each other. But we can have other numbers relatively prime with respect to each other. For example, 8 and 27 are relatively prime. Their greatest common divisor is 1.
But 8's not prime.
8's not prime. 27 is not prime.
How is 8
But
prime?
how is 8 not prime? That even number 8?
Even numbers can be prime.
2 can be prime.
2 and 4.
4 is not prime. It's 2 times 2.
The greatest. Okay. I get it.
Okay. So, that's what we mean by relatively prime. So these two numbers, 431 and 29, were relatively prime. Well, obviously, because 29 is prime.
So it's just because one of them is prime and that makes them relatively prime?
Yeah. A prime number and a number that aren't prime can either that number has to be a multiple of the prime number or the greatest common divisor has to be 1.
We always know what the greatest common factor is. The divisor is if one of them is prime.
No. It is either the prime number or it's 1.
So you could just do math.
Yeah, if it happens to be a prime number, but that just gets you the GCD. That doesn't help you figure out the x and the y.
Yeah.
Okay, you know the GCD is 1. Great. You still got to find the x and the y. Every time. I'm only going to ask you to do that. What's the point of just finding the GCD? That's not fun. Alright. Corollary. Corollary, there exist integers x and y such that ax plus by equals 1 if and only if a and b are relatively prime. Right?
Yeah.
Because we can always get x and y that give us the greatest common divisor. The greatest common divisor 1 is relatively prime, so I didn't even bother writing anything. That one's just obvious. But let's make it explicit. Good?
Yeah.
And one more quick proof. Let D be the GCD of A and B. If E divides A and E divides B, then E divides D. So D is the greatest common divisor of both those things. If E is also a common divisor of both those things, then E divides the greatest common divisor.
Didn't we prove that? Like,
No,
right there?
all we proved is that if E is a common divisor, it's less than or equal to D. But we didn't know that E is actually a divisor of D. We didn't prove that.
We did it right there. Look at number 10 of your proof.
You're right. Where D was expressed that way, and D will be able to be expressed that way here as well. So yeah, it's the exact same thing. Observe that there exists x and y such that D is equal to those things. Since E divides that and E divides that, D divides D.
Yes. You need to move your camera. You're starting on that side.
Of course we're starting on this side.
Okay,
Let's do break real quick while I reset the camera, and then when you come back, we'll start modular arithmetic.
okay.
That looks
I can split this into 2 points.